Hello, welcome back to Algebra. The title of this lesson sounds really intimidating, but I promise you it's not going to be a big deal. It's called Factoring Perfect Square Trinomials and Difference of Two Squares, Part 1. So basically what's going to happen here is I'm going to review some of the special products of binomials that we've done in the past. This is stuff that we've already covered a long time ago. We learned how to multiply using these special products. And then I'm going to show you how we can use what we've already learned to factor expressions, which is what we've been doing in the last couple of sections. And it's something that you might not realize you can do until you see it done. But it's just like everything else in math. I mean, nobody here is born knowing this stuff until we learn it and practice it. So what we're going to do is we're going to learn how to factor these things called perfect square trinomials. We'll explain that. We'll also explain what the difference of two squares is. So to get the ball rolling, first I want to recall. So everything that follows here is basically going to be things that we have talked about in the past. So I want to recall, we've talked about how to multiply something that looks like a plus b times a minus b. Now don't forget, a and b can be anything. This could be x, this could be 2. So it would be x plus 2, x minus 2, or y minus, y plus 3, y minus 3, something like this. But when we have something of this form, we've already talked about the fact that it can be simplified to a squared minus b squared. We've already done that in the previous lessons on special products of binomials. Now we've also talked about the special case when you have a binomial a plus b. Again, a and b can be anything, and you square it. When you do the FOIL and you simplify all the terms, it ends up turning out to be the following: a squared plus 2 times a times b plus b squared. Now again, keep in mind, a and b can be anything. So you just stick in whatever a and b is, and then this is going to be what it is. And then similarly, we talked about the case of what if it's a minus b squared. And it looks really, really close to this one. It's a squared minus 2 times a times b plus b squared. So if you've never seen these three relations on the board, it just means you haven't watched my lesson on those concepts, which was special products of binomials. So you need to go back and look at that now. But I'm starting from the point that you've seen these before because we've covered it before. Now it turns out that these two guys are multiplied and it can be simplified to this. This is squared, which means a plus b times a plus b can be simplified to this. And this is a minus b times a minus b, which can be simplified to this. So if you remember from the last section, we said that the concept of factoring is basically the reverse of distribution. In other words, if I have a big expression here and I'm told factor this expression, what I'm really trying to do is find some other expression that consists of things that are multiplied together to get me what I'm starting from. And we've done a bunch of examples of factoring in the last section. So the way we started it is we said, here's a big expression, try to find something common to all of these things, pull it outside the parentheses, and we'll create something that can be multiplied together to give us that. So what I've been telling you was factoring is just distribution in reverse. We're going to try to take it and create something that we can then distribute back in to being the function. So here we have some special cases. We have multiplication giving us this. Now what we're going to do is use this to go backwards. So let me draw like a little line here. Let me tell you that there's going to be something you're going to be told that you need to learn how to factor, and it's called this. It's called the difference of two squares. And the difference of two squares, let's do it in a different color. The difference of two squares means that if you're given something like this and told factor this expression, a squared minus b squared, where again, a can be anything and b can be anything, but whatever it is, it's something squared minus something squared. That's why it's called the difference, because it's subtracted, of two squares. Obviously, you have two things that are squared. So if I tell you to factor this, the first thing you're going to say is, it's impossible to factor, because I've been telling you all along, to factor things, the first thing you do is you look at every term and you try to pull out things that are common to all of the terms. So you look at this and you say, well, here's an a squared, here's a b squared. There's nothing in common, so I can't pull anything out, therefore it's not factorable. However, this is a special case, and you also have to think about the big picture of what factoring is. Yes, we do try to pull things out. Yes, that's what we talked about before. That's the simplest type of factoring. but the broader definition of factoring means distribution in reverse. We want to see if we can write an expression so that we can then multiply things together to get that expression back. We want to find two or more things to multiply together given what we started with. Here's what we're starting with. But look up here. This is exactly what this is. This, by definition, is equal to this. So without even doing any math at all, if we're given the difference of two squares, we know that its factored form is a plus b times a minus b. And your mind is going to be blown for a second because you're going to say, well, wait a minute. He didn't look here and pull anything out. He just wrote this down. That's why I've been trying to tell you the big picture definition of factoring is distribution in reverse. If I give you this and I say, multiply it out, then you'll do this times this, this times this, this times this, this times this. Simplify, what will you get? This. So distribution, this thing in reverse will give us this. Another way to think of it, we want to find anything we can that will consist of two or more things that we can multiply together to give us this. Because this is a special case, because we've already covered this, we already know from this table that any time I have an expression that is a squared minus b squared, the factored form, which means two or more things multiplied together to give me that, is always going to be of this form, right? So even though we cannot find anything to pull out, which was the simplest type of factoring, when it's a special case, one of these, we can write the factored form down directly. All right, so that's one that we're going to have to remember. We'll leave that on the board. And then there's another type of special case. We obviously already have it on the board. It's called perfect square trinomial. Perfect square trinomials. Why does that mean? It sounds really, really complicated. But it's not complicated. What we're basically saying is, what is a trinomial? This is a trinomial because it has three terms. This is a trinomial because it has three terms. So just like you know that, I'll go way over here, just like you know that 4 is a perfect square. Why? Because you can take the number 2 and raise it to a square, and that will give you 4. You know that the number 36 is a perfect square of 6. You can square it because it's these perfect numbers. There's only certain numbers that are perfect like that. 100 is a perfect square. Why? Because I can take 10 and square it and I can get 100. But 7's not a perfect square. 14's not a perfect square. I can't take a number and raise it to the second power and get 14. I mean, I know 7 times 2 is 14, but that's not squaring, right? We need to find a number times itself to give us that number. So only certain special numbers can be perfect squares. Well, it turns out that certain special trinomials that are written exactly like this can be perfect squares. Notice how I told you this guy is special because I can say 6 squared. Well, this trinomial is special because it can be written as a plus b squared. This one's special because it can be written as this squared. In general, the trinomials that you have will not be perfect, just like most numbers are not perfect. I mean, 5 is not a perfect square. I can't take a number and raise it to the second power and get 5. But I can take 49, and that's a perfect square. Why? Because 7 squared, 7 times 7, is 49. It's a little bit of a perfect case, special case. So basically, we just need to take these special trinomials and write them backwards and basically say, if we come across a trinomial that's perfect like this, perfect square, in other words, if we're given a trinomial of the form a squared plus 2ab plus b squared, then we know without even factoring anything out term by term that it's one of these special cases, and we can always write it as a plus b squared, like this. And if we come across a trinomial that looks like this, a squared minus 2ab plus b squared, it's a special case trinomial, and it's going to be a minus b squared. So I want to make this a little bit clearer right here, so let me kind of draw my parentheses a little bit clearer. A plus b squared, a minus b squared. Now, again, I said most trinomials are not perfect. Why? Because look at how perfect this thing is. You have to have a trinomial where the first term of it is actually a square. And also the last term of it is also a square. And also the middle term has to be 2 times whatever this a is times whatever this b is. So just forget about this bottom one down here. It has to be very specially constructed in order to be exactly that. If you have something squared and something squared on the end, but the middle is not 2 times the first thing times the second thing, then it's not a perfect square. It will not turn out to factor into this. Only when it's exactly like this. Same thing with the bottom one here. You have to have a square in the first term, a square in the third term, and the middle term has to have a negative sign, 2 times whatever this base a is times whatever this base b is. Only then is it a perfect square trinomial. That's why it's called perfect square trinomials, because only then is this the case. Why is it like this? Well, that comes back to the previous lesson we've done. When you take these binomials and square them, multiply them by themselves, you get cancellation of terms, you get nice interior terms adding, and then it turns out to be one of these. That's why I said in the beginning that if you haven't seen the lesson on this, then you need to go back and do that. So I'm going to leave this on the board. This is what we're going to do. We're going to learn how to factor using these special cases. The difference of two squares is this rule, and perfect square trinomials is this rule. So let's stop talking about it and just do a couple of examples and show you how to apply these rules. So for the first one, you might say, how do I do this? 16x to the third power minus 64 x squared. Now this is a little bit of a trick question. It's kind of a warm-up problem because the very first thing you should do whenever we try to factor anything is you try to look term by term and see if you can pull anything out that's common to both terms. And if you can, then you do it. You factor it that way, which is what we've done in the last couple of sections. But when you finish that, the next thing you should do is look at what you have left and see if it's one of these perfect special cases. If it is, then you can factor it even further. And so first thing we do is we say, well, we have 16 and 64, and I know right away that 16 times 1 is this, and 16 times 4 is this. So 16 can come out as a number. I have x cubed and x squared, so I can pull out an x squared. And so when I go here, it's going to be times 1 and then times x to give me x to the third. I have to have a minus sign, 16 times 4, and then I have an x squared. So there's an x squared here, so I don't have anything else further to do. It's 16x squared times x minus 4. This times this gives me this. This times this gives me this. Of course, the minus sign is there. Well, this wasn't a perfect square trinomial, and it wasn't a difference of two squares. The reason I'm putting it there is to remind you that the first thing you do when you factor anything, try to factor out any common terms and look at what you have left over. Okay? What you have left over is just x minus 4. That's not a trinomial at all, and it's not the difference of two squares because the first term isn't even squared. So there isn't anything that I can do beyond that. This really didn't use any of the new rules that we have. It was more of just a review for you. Now the next question will, what if I have t to the second power plus 18 times t plus 81? The first thing you do, and I tell you, factor this expression. When you see the word factor this expression, what you need to do in your mind is think, I'm going to do distribution in reverse. I want to find two things that multiply together to give me that polynomial. So the first thing you do is you say, let me pull out any common terms. T squared, t, no t at all, means I cannot pull any t's out. Just number 1, 18 and 8, 81. There's nothing I can pull out other than 1, and that's not going to help me. So really, I can't pull anything out. So it looks like, basically, you can't factor it at all. But then here's the big clue. Here's the big clue. When you have a trinomial like that, you should try to see if it's a perfect square trinomial. And remember, all of these perfect square trinomials have the first term of that trinomial squared, something squared, and the last term has to also be something squared. So we look at our problem and we see, well, the first term is squared. We look at the last term, 81. Now, your first thought is, well, 81's not squared. But what you should think about is 81 is a special number. Why? Because it's 9 squared. So there's certain special numbers that should jump out at you, right? Because let's just go through them real quick. 2 times 2 is 4, so 4 is kind of one of those numbers. 3 times 3 is 9, so 9 is another one. And then you have 16 because 4 times 4 is 16. And you have 25 because 5 times 5 is 25. You have 36 because 6 times 6 is 36, and so on. 49, and then 8 times 8 is 64. 9 times 9 is 81. 10 times 10 is 100. And you can go on beyond that. But those are all what we call perfect squares. And so this is one of them. It's 81. So we have the first two constraints listed here. And just to show you, we do in the next step, just to kind of show you how it's going to basically go, is I'm going to write this as t squared plus, I'm going to leave the inside alone, and I'm going to write this as 9 squared. So you can see that the first term is squared, the last term is squared, just like it says it has to be. The first term is squared, and the last term can be written as something that is squared. That's the way to think of it. So in this problem, A is t in our problem. B actually is just 9. It's whatever happens to be the thing that's squared. But then according to our rule, the middle term of this trinomial, if it's going to follow this rule, must be able to be written as 2 times whatever a is times whatever b is. So let's just see if that's true. If the middle term is 2 times a times b, then it will be 2 times whatever a is, which is t, times whatever b is, which is 9. And that actually does multiply together to give us our middle term. So the reason I'm writing all this stuff down is because the first step is to figure out if it actually is a perfect square trinomial. You know, with numbers it's easy because you know that 5 times 5 is 25. You memorize that. So you know 25 is a perfect square. You know 100 is a perfect square, 10 times 10, right? But with trinomials, you don't know, so you have to figure it out. So we say first term is squared, last term is squared. Is the middle term 2 times t times 9? Yes, it is. That equals 18t. So then I know I have a perfect square trinomial. So because I know that it fits the form, then I can literally write the answer down without any calculation at all. Because the answer says that if it's a squared plus 2ab plus b squared, then the answer will be just simply a plus b quantity squared. A is t plus b, 9. That's the base that happens to be squared there, quantity squared. That's the factored form. There is no way that a person new to algebra will be able to look at this trinomial and know automatically that the answer is t plus 9 squared. I don't believe it's possible unless you're just really amazing at math, prodigy, or something like that. It's not something any of us can see. So just break down the mysteries of, oh, I'm not good at math. No, we all have to figure this stuff out. We have to look at the rule and say, well, this is something squared. This can be written as something squared. Then it follows the formula because this is the case. If the interior term, for instance, were 19 times t, then this wouldn't be a perfect square trinomial and this wouldn't even be correct at all. You would not be able to factor it like this. But the interior term is exactly as the rule says, so then we can do that, t plus 9 squared. And then if you want to check it, which I always kind of encourage you, I'll just check it real quick. I won't do this for all problems, but t plus 9 squared is t plus 9 times t plus 9. And we all know how to multiply this. T times t is t squared. T times 9 is 9t. Then we move here. 9 times t is 9 times t. And then 9 times 9 is 81. We can add these and give us 18t, which is the middle term and the first and last terms match. So when we multiply out our answer, we get back what we started with, which is exactly how every one of these problems should go. All right, now I talked quite a bit on this first problem. We're not going to do as much talking for the next problems. What we are going to make sure everybody understands. So we have z squared minus 12z plus 36. It's a trinomial, so the first thing we try to see is it a perfect square trinomial? The first term is squared, obviously z squared. The last number should immediately ring alarm bells. It's a square because 6 times 6 is 36. You cannot have a perfect square trinomial unless this last thing can be written as something squared. So we can say that this is z squared. Let's go ahead and keep the middle term exactly as it is for now, minus 12z plus 6 squared. It's helpful to write it like this to make sure that first term squared, the last term squared. Okay. Now, is the middle term follow the rule? Z squared, which means it would have to be, there's a minus sign here, so we're going to follow this rule. It has to be a squared minus 2 times a times b. That would be minus 2 times z, that's a, times b, which is the whatever squared in the last part, which is 6. Plus 6 squared. Now look what you have here. This is going to give you minus 12z. So the middle term is, or does, make everything perfect a perfect square, which means I can apply my formula. Which basically means you can write the answer down completely because the perfect square trinomial means when you have this form, it's a minus b squared. Which means the first term, a, minus whatever the last term here was, b squared. Z minus 6 squared. So again, just to caution you, this interior term was minus 12z. If it happened to be minus 10z or minus 11z or minus 97z or anything else, then this wouldn't be a perfect square trinomial at all. Or if this last term were not 36, if it were 37, it wouldn't fit the map at all. Now, if you take and multiply this out, you'll have z minus 6 times z minus 6. And you can see the first terms are going to give you z squared. You can see the last terms are going to give you negative 6 times negative 6 will give you a positive 36. Now the interior terms, let's just write it like this. Z squared, which is this one. Then you have z times negative 6 would be negative 6z. Then you have this one, negative 6 times z is negative 6z. And then negative 6 times negative 6 is positive 36. You can see these will add to give us negative 12z, which means that my answer is correct because everything else matches what the problem is. All right, so far we followed these two rules. If it's a trinomial, check and see if it's a perfect square. If it is, you can write down that this is the factored form without ever pulling anything out of each term, because factoring in general is really just trying to find things that multiply together to give you what you start with. That's really what it is. And these are special cases. They're not common, but they are important. So let's move on to the next one, where we will make use of the very first rule that we have, the difference of two squares. A squared minus b squared is a plus b times a minus b. All right, so what we'll do is we will then say, what if I had a problem 16x squared minus 1? So you look at this and I tell you, hey, factor this expression. The first thing you're going to tell me is I can't factor that because 16 is here, 1 is here, there's nothing in common to pull out. X squared is here, there is no x here, there's nothing to pull out, there's nothing to do. The next thing you should do after you try to pull things out is see, is it one of these special cases? At first it doesn't even look like a special case, but you think about it carefully, what it means is you have to be able to write it as something squared minus something squared. Well, if you think about it, this first term should ring alarm bells because 16 is a square of 4. So I can write this as 4x quantity squared. That's really what the first term is because 4 squared is 16 and x squared is x squared. So the quantity a squared minus b squared, a is just the whole entire quantity 4x. That's what has to be squared in order to give me this back. Minus, it has to be a difference, and 1 is a perfect square also because it can be written as 1 squared. So you see, even though the problem doesn't look like a difference of two squares, it actually is the difference of two squares because a squared minus b squared, where a is 4x and b is 1. So once you've identified that it is the difference of two squares, and you know that it's a squared minus b squared, then all you have to do is write, what's the rule? When you identify it's a difference of two squares, it's just going to be a plus b times a minus b. Now we know what a and b are, so we write it simply as 4x plus 1 times 4x minus 1. That's the factored form. Because remember, factoring means I'm trying to find two things or two or more things that multiply together to give me what I start with. And I'm claiming that this is actually equal to this stuff multiplied together. And if you want to check that, which I encourage you here in the beginning to do, I would check it as follows. I would say 4x plus 1, 4x minus 1. First terms, 4 times 4 is 16x squared. This times this is just times negative 1, so it's negative 4x. These two terms are positive, so it's just going to be positive 4x. And then these last terms, 1 times negative 1 will just give you negative 1. These cancel. So all you have is 16x squared minus 1. It's exactly what I started with. But the key is trying to always write it as a difference of two squares. All right, let's see what else we have here. Just a few more problems to get a little practice. Two more, actually. We're going to have a trinomial here. Let's see if it's a perfect square trinomial. We have 4x squared plus 20 times x plus 25. And I say factor this trinomial. First thing you do is you try to pull something out of each term. 4, of course, I could pull out of 20. That works, but it doesn't work for 25. I can't pull out 2 from everything either because it doesn't go evenly into here. And also, there's no x in all terms, so I can't factor out a single term to the outside. So the next thing I do is I say, is it a perfect square trinomial? Which means that it has to be written as first term squared, last term squared, middle term has to be a special relationship there. Well, 4 can be written as 2 times 2. So I can actually write this first term as 2x quantity squared. The square will make this a 4. The square will make this make an x squared. Now I'm going to leave the middle term alone for now. But the last term, this should ring alarm bells, right? Because 25 is a perfect square. I can write that as 5 squared. So far, it looks pretty good. But I need to check that middle term. I need to specifically make sure that this middle term can be written as 2 times a times b, where a is 2x and b is 5. 2 times 2 is 4, 4 times 5 is 20x, which is exactly what the middle term is. So this trinomial doesn't look perfect. It doesn't look like an amazing square, but trinomials are different than numbers. You have certain things to check for. This can be written as a perfect square. This can be written as perfect square. And the middle term has to be written as 2 times this times this. Once you have convinced yourself that that's the case, then you just write it as a plus b squared. That's what the rule was. A was 2x plus b, which was the last term, a base quantity squared. So this is the final answer. So if you were to write out the FOIL, this times itself, and cross multiply all the terms, then you would get the first answer here. But also remember, we learned how to square binomials a little faster. You take the first thing and square it. That's going to give you 4x squared, right? Then plus 2 times the first term times the last term. We just did that here. 2 times this will give you 4x times this is 20x. That gives you this term. And then plus this squared gives you the last term. So you can do it in your head, actually, when you get enough practice by seeing that squaring this actually does give you that, and that is the factored form. All right, one last one. It's going to be 16x squared minus 25. Obviously, it's not a trinomial, so the first thing we're going to do is see if it's one of these other special cases. Can I pull out something common to both? No. This is 25, this is 16. There's nothing that I can see in common that I can pull out of both of those terms because there's not even an x there. So then I check, well, it's not a trinomial, doesn't follow that. Is it a difference of two squares? If it were to be a difference of two squares, I would have to be able to write the first term as a perfect squared and the second term as a perfect squared. But I can write that first term as 4x quantity squared. That'll give me the 16x squared. I can write that second term as just 5 squared. So it is the difference of two squares, right? Which means that the final answer will be a plus b times a minus b, which will be 4x plus 5, 4x minus 5. That's the final answer, 4x plus 5, 4x minus 5. And if you multiply this out, you can see that it's correct. You're going to get 16x squared here, and then you're going to get the negative 25 from here. The interior terms are going to give you 20x, and these exterior terms will give you negative 20x, so they'll add and go to 0. That's why there's no middle term there. So the name of this lesson was quite, I think, intimidating sounding. It's called Factor Perfect Square Trinomials and Difference of Two Squares. Sounds very, very complicated, but really, it's the exact same multiplication rules that we've already learned in the past, but in reverse. So just like we learned the special products and how it can be simplified very easily if they follow certain patterns, all you're doing is going backwards. You're saying, identify these trinomials as being special, then you can write the factored form very easily. Identify this difference of two squares as kind of a special case, and then you can write the factored form very easily. So make sure you can do these. Follow me on to the next lesson. We'll get some more practice. This kind of stuff is really, really useful for solving certain types of equations that we'll be doing later on. So make sure you get it. Follow me on to the next lesson. We'll get more practice right now.